Hey there, and welcome to The Explainer. Today, we're going to go on a bit of a math detective investigation. Our mission? To uncover the secret rules that make numbers tick. And believe me, our first case is already waiting.
So let's kick things off with a puzzle. Now, this might look like a simple addition problem, but the answer actually cracks open one of the most fundamental rules in all of mathematics. We're going to solve this thing together, and by the end, you'll see exactly how it all connects.
All right, so before we can even touch the rules, we got to know who we're dealing with, right? Every good investigation starts by identifying the key players. And for us, that means getting to know the rational numbers. You can kind of think of numbers like this big, growing family tree. We start with the simple natural numbers, the ones you count with. Then you pop in 0, and suddenly you've got the whole numbers. Throw in their negative buddies, and now you're dealing with integers. But the family we're really focused on today, the rational numbers, well, they're the next big branch, covering all of these and a whole lot more. Okay, so here's the bottom line. A rational number is basically any number that you can write down as a fraction. That's the key. So, of course, that includes simple stuff like 1/2, but it also includes whole numbers, like 5, because you can just write that as 5/1. It's a really big family.
All right, we've met our key players. Now it's time to open up the rulebook. We're about to uncover 5 fundamental properties of addition that tell us exactly how these rational numbers play together. Think of these as the secret codes of math.
Our first clue is something called the closure property. I like to think of it like a private club. If you take two members of the club, in this case, rational numbers, and add them together, the result is always another member. You can't add two rationals and end up with something that isn't rational. The group is closed. Let's put this to the test. We take two perfectly good rational numbers, 2/5 and 1/3. We add them up, and we get 11/15. And what's that? You guessed it, another rational number. The club door stays shut. It works. Next up is the commutative property. You know, this next one is probably something you already feel is true. It just says that when you're adding, the order doesn't matter one bit. It's kind of like your commute to work, right? Going from home to work is the same distance as going from work back home. So you see, whether we add 3/4 to 5/6 or we flip it and add 5/6 to 3/4, it makes no difference. We get the exact same answer, 19/12. The order can be swapped and the math doesn't even blink.
Okay, now for the associative property. And hey, this is the one that's going to solve that puzzle we started with. This rule tells us that when you've got a list of numbers to add, it doesn't matter which pair you decide to associate or group together first. And boom, there's the proof. We solved our original puzzle from both angles. First, we grouped the first two numbers, and then we grouped the last two. And look at that. No matter how we group them, both paths lead us straight to 14/12. The associative rule is legit.
Okay, this next idea is really cool. It's the concept of an identity. In math, an identity is something that leaves another number's value completely untouched after you do something to it. And for addition, 0 is the magic number. It has that special power. So take any rational number you want, say 2/9. What happens when you add 0 to it? Yeah, absolutely nothing. The number's identity stays exactly the same. 0 is kind of like the do-nothing hero of addition. All right, our final rule is the additive inverse. And trust me, this is a really powerful idea. It means that for every single number out there, there's a perfect opposite, like a mirror image, that when you add them together, they completely cancel each other out and take you right back to 0.
So for 2/9, its perfect opposite is... You got it, -2/9. You add them together, and they just, poof, cancel out to 0. It's a perfect inverse pair.
All right, detectives, we have gathered our clues. We understand the 5 key properties. Now, let's put these rules to work and crack a case to see why they're so powerful in the real world. So here's our case file. It's a word problem. Manish went for a walk on Monday and then again on Tuesday. Our job is simple. Find the total distance he covered. So, to solve this, it's pretty straightforward. We just need to do one thing. Add those two rational numbers, those two distances together. And this is where knowing our rules really pays off. Because of the commutative rule, we know it doesn't matter if we add Monday's distance to Tuesday's or the other way around. So we find a common denominator, which is 12, add the fractions, and boom, we've got our answer, 19/12 of a kilometer. Case closed. Okay, so we've seen the rules, we've even used them to solve a problem. But what's the big takeaway here? I mean, why does any of this really matter?
Well, look, these properties aren't just for math quizzes. They're kind of like the invisible skeleton that holds up all of higher math. They give math its consistency, its predictability. They're the reason algebra works, and they allow us to solve real-world problems with confidence.
You know, getting a handle on these properties is a huge step. It's about learning to see the hidden structure underneath everything. And that kind of leaves us with one last question to chew on. Now that you've seen the hidden rules of math, what other invisible rulebooks are shaping the world around you every single day?